selection problem. From the name, you can see what kind of problem we are going to study. First, it is a selection problem. I have not explained this type of problems, selection problem. Yeah, minimum. Yeah, from this name, you can see the content, finding the minimum of an array. Yeah. All right, so let's start. Yeah. Problem number 3, find the minimum of an array. That's the title. Let me give you the question first. Given an array, this our usual representation, capital A array, yeah, with n elements. Yeah. Here, this array, I didn't mention it is ordered or unordered. That means unordered, right? Yeah. If I do not say ordered, then we just assume it is unordered. Yeah. Because you cannot add extra information. If you assume it is ordered, that means you add extra information. We cannot add any information to it. So then that means it is an unordered array. Yeah. Question. Find the index I such that A of I is the minimum of the array. Very simple, right? Still a simple example. But I can use this example to introduce many important concepts. Yeah. Actually, this question is very important for this class. Later, I will refer to this question several times. Yeah. Pretty important. Yeah. All right, so let us do some analysis. Yeah. First, the problem type. Yeah, so it is selection type. This is the first question of our selection problem. Yeah. But what is the selection problem, right? You may like to know what is the definition of the selection problem. Yeah. So let me give you the definition. Very simple. Yeah. One line. Yeah. This one sentence, you get a definition. Yeah. Find the kth smallest element in a given array. Kth smallest, that's it, right? Remember, given an unordered array, find the kth smallest element. That's the definition of the selection problem. But k must be given. Yeah. All right. Our minimum problem, the k equals 1. That is our minimum problem. K equals 1. Yeah. Here I also give you the reference in the textbook. Yeah. The content about this selection problem. Yeah. All right. Let us do some analysis. Yeah. First, let's look at the solution. The solution is simple, straightforward. Yeah. Let us quickly go through the solution first. We do initialization. Yeah. So we create a variable called this main variable, and we store first element as its initial value of 0. Yeah. Then after that, then we define our general step in this way. Yeah. We compare main variable with the current element, A of I, the current element for processing, A of I. We do comparison. So when we do comparison, we have these two possibilities. First, main greater than A of I. Yep. That means we find a smaller element, right? Let me just admit it. All right, yeah. So we need to update this variable by the current element A of I. So we assign A of I to this variable. Otherwise, if min less than or equal to A of I, then we should not update min variable, right? Yeah, we do iterations. Yeah. We go to the next element, A of I plus 1, yeah, and do comparison, then, you know, do our regular comparison work. Yeah. Eventually, you will reach the end of the array. Yeah. The last element in the array, that is I equals n minus 1. Yeah. So after you complete the comparison with main variable with the last element, then you get your final answer. Yeah. So finally, you return the value stored in the main variable. That is the whole algorithm, right? That is the whole algorithm. Yeah, nothing new. Yeah. So by our intuition or our experience, we can find the solution easily. Yeah. But the point here is not a solution. The point here is another important question. Yeah. So in our next slide, we will discuss about that important question. Yeah. All right. Here, let us count the number of comparisons. How many comparisons do we need to find the answer, the minimum value? Yeah. Can anyone type answer in the chat area? It is a simple answer, short answer. Yeah. We know we have n elements. N elements. The total number of elements is n. How many comparisons? The answer is related to n. Can anyone type the answer? Just a close guess. As close as possible. Good. Yes. n minus 1. Exactly. All right. Yeah. Too simple. Yeah. Yeah. The reason I ask you this question, because I want to see if some of you may type n, right? If some of you may type n, not n minus 1. Actually, it's n minus 1. Yeah. Not n. Because the first assignment, look at the first assignment. It is an assignment operation. For the first element, we do not do comparison, right? All right. You got transcript. All right. Enable transcript. All right. For the first element, we do not do comparison. We do assignment. So we do not count it. All right. Here, my question, I only ask you number of comparisons. Yeah. So we ignore all the assignment operations. Assignment also operation. All right. Yeah. But we ignore. So you should exclude the first element. Then for the remaining elements, each one, you need to do one comparison. That's n minus 1. Yeah. All right. Okay. Yeah. Then the answer, n minus 1. All right. Yeah. All right. So we get the answer. But the most important question is, let's look at the next slide. Yeah. We need to ask this question. Is it possible to further improve the algorithm? Right? Yeah. Last time I said, every time when we find a solution of a computing problem, we always need to ask this question. Yeah. If there is any room to do the improvement, here we should do the same thing. Yeah. But in the general situation, for this question, basically we have two cases. Two options we can use for this question. The first one, improve the algorithm. Right? Try our best to do more investigation, try dig deeper into this question and find a better solution. That is one option we can do, but you may not be able to improve it, right? Yeah, it's possible you may not be able to improve it. Yeah. So we should have the second option. Yeah. If we cannot improve it, we can try the second option, convince people that this is already optimal. The current algorithm is already optimal. Yeah. So that gives us a new concept, optimality of an algorithm. So this algorithm cannot be improved. Nobody can improve this algorithm if it is optimal, right? Yeah. So that's today, in this part, we will do our option number 2 here. Yeah. But convincing people is not easy, right? So you have to make very strong arguments to convince people. Yeah. So let's do that part. Yeah. Optimality. Look at this optimality issue. Yeah. The harder part. Yeah. Why the optimality issue is so hard. Yeah. So here, let me point out why it is so hard. Yeah. If you claim one algorithm is optimal and it cannot be improved by anyone in the world, right? Yeah, that's the basic definition of optimality. Nobody can improve it, right? Nobody, not just in our class, not just in this country, not just in the whole world, right? Because even if nobody in the world cannot improve this algorithm, can you guarantee that after several generations, there is some very smart person who can improve it? How can you guarantee that, right? So even if we want to say, if we want to convince people it is optimal, we need to also prove even in the future, nobody can improve it. That is the meaning, exact meaning of the optimality. Yeah. Even in the future. So now you can see how hard it is, right? So that is one aspect of, yeah, why it is so hard. Yeah. But another aspect, all right, we need to consider all the possible algorithms for this particular computing problem, all the possible algorithms. Yeah. Yeah. Then those algorithms cannot improve this kind of performance we can get for this one. Yeah. And especially those algorithms, including unknown algorithms. Unknown, because there are many algorithms that have not been developed, right? Many, for this particular computing problem, there are many unknown algorithms. Unknown, I mean, future problem solvers, they can develop new algorithms to solve this particular computing problem, right? Yeah. You cannot predict how other people in the future, they can still solve this problem in a better way, right? Yeah. So including unknown algorithms, we need to cover. We need to cover how hard it is. Think about that, how hard it is, right? Yeah, yeah. So you may wonder, is it doable, right? Yeah, so I mentioned several aspects. It is so hard. Is it doable? Yeah. Yes, it is doable. Yeah, That's the main topic of Part D. It is doable. Yeah. So the first question, how do you study unknown algorithms? How do you study unknown algorithms? It is unknown. How can you study it, right? Yeah. Think about that. Based on your experience, based on your logic, how can you study an unknown algorithm? Is it possible? Right? Pretty tricky. Yeah. Yeah. The question, is it possible to study unknown algorithms? Think about that. Is it possible? Right? Yeah. Based on intuition, you may answer it is impossible, right? If it is unknown, how can you study it? Right? Yes. But can you imagine there is a special situation that people can still study unknown algorithms? Yeah. The answer is yes, not no. Yeah. All right. So let me just adjust my laptop position so I can write it better. Yeah. All right. Yes. So look at how tricky it is. So first, the answer is yes. Not no. Yes. Okay. Yeah. You can see in this class, we will do many smart things. Yeah. Here, this is one. You have to do something very smart to answer this tricky question. Yeah. All right. So let me give you the main point here. Yeah. The main point. Why we can study unknown algorithm. Yeah. Yeah, let me write this idea short. Yeah. Study. Yeah. So not study. Yeah, study is okay. Yeah, but let me write discover. All right. Yeah. Discover some general property that covers unknown algorithm. How about that? All right. Discover some general property. That property can cover unknown algorithms. If you can do that, then you can study and you can make your conclusion. Yeah. I show you example here in our problem number 3. I show you how can we do that. Yeah. All right. In my next slide, I will make convincing arguments using some special property. Yeah. Or general property. Yeah, special or general, relatively, right? Yeah, with respect to something, yeah, general or special. Yeah. All right, so let's look at the convincing part. How do we convince people that our algorithm is optimal? Yes, yeah. We need some imagination based on our real world experience. Yeah. Yeah. I emphasized this point several times. Yeah, many times when we do thinking, we need to connect to our real world experience. Yeah. Here, it is another example. Yeah. Let me use our real world experience corresponding to our comparison operation. Because here, our main object to be studied, comparison operation. Yeah, we studied this operation. Yeah. This operation, we want to connect to our real world experience in a sport game. Yeah. In a sports game, a match in a sport game, a match between two players. Yeah. There is some analogy between these two objects, comparison object and sports game match in a sports game object. Yeah. Because we can do this kind of analogy between these two objects. Less than, yeah. In comparison, we have a less than result. Then it corresponds to win in a match. Yeah, less than win because I will go finding the minimum, right? The smaller the value, the better, right? Yeah, so we define if the first value, the first number is smaller than the second number, then the first one wins the game. Yeah, wins the match. How about that? Yeah. So that is the, relationship we want to establish here. Right. Equal, that's tie. Yeah. Greater than, lose. Yeah. So with this kind of connection, then we can understand our arguments using our real life experience. Yeah. All right. Now it is the time I make this convincing argument. Yeah. There are several steps, so I hope you can follow my statements one by one. Yeah. All right. The first one, imagine that the main is the final winner. Yeah, the smallest one. Yeah, that corresponds to some player. That player in a sports tournament, that player should be the final winner. Yeah. All right. Yeah, that's the first sentence. Yeah. Second, it needs to beat all the other elements in the array through comparisons, directly or indirectly. Yeah. The winner, you have to beat everyone else in this tournament, right? Yeah. So that's the way we define the final winner, right? Otherwise, how can you win the championship, right? How can you win it? Yeah, yeah. But here, look at this directly or indirectly. Directly, we know this main player beats another player. That's the direct winning, right? Direct win, yeah. But indirect, yeah, there is a situation the winner beats another player in an indirect way. So what's that? Let me give you an example here. For example, we have this case. Let me use less than. Yeah, less than means winning, right? Yeah. So A less than B. That means A beats B, right? B less than C. That means B beats C. Can we have the conclusion that A less than C? Yeah. In math, in inequality, we have this property, right? Transitivity property. In math, this result corresponds to transitivity property. Okay. In the real world, we do not have it, right? Think about that. This is something different. When we connect to the real world experience, we have to modify a little bit. Not 100% the same. Here is the key difference. In the real world, you can now say A beats B, B beats C, then you just say A always beats C, right? We cannot say that. Sometimes A may not be able to beat C in the real world, right? Yeah. But in math, we can say that A always beats C. A always less than C by transitivity property. All right. Yeah. Here we have to take this property in our convincing arguments. Yeah. All right. So that means indirectly. Yeah. In this situation, this indirect, we allow this happen. Yeah. We allow this situation to happen. Yeah. In this way, we do not need to arrange another game, another match between A and C. Yeah, because we waste our resource. We do not need to arrange a match between A and C. We want to save resource. Yeah, so we can claim A beats C indirectly. All right, that's our rule. All right, that's our rule. All right, yeah. Then we go to the next statement. If an element loses once, it is eliminated. Yeah, because our goal is to find a final winner. Right? Our goal in this problem number 3, our goal is find the final winner, nothing else. Yeah. Then, if one player loses to anyone, that player must be eliminated immediately. All right. Yeah. Yeah. So that's the third statement. Yeah. Next one. Each comparison can only eliminate one element. How about that? Each comparison. Yeah. One winner, one loser. That loser is eliminated. Can you eliminate the winner? You cannot, right? Yeah. How can you eliminate a winner in that match, right? Yeah. So we have this statement. Each comparison can only eliminate one element. Yeah. All correct. Yeah. So far we have 4 statements. Yeah. They are all correct, right? Yeah, no question. They are all correct. Yeah. The next one. Yeah. We need to eliminate n-1 elements. Yeah. To get a final winner, there are a total n elements, n players. To get a final winner, only one player can be the winner. The remaining n-1 players all must be eliminated. Right? Yeah. So we need to eliminate n-1 elements. Yeah. Thus, we need at least n-1 comparisons. Think about our last statement. This is our last statement. Yeah. So the algorithm, any algorithm, in order to find the final winner, the minimum value, you have to do at least n-1 comparisons. That is the final conclusion. At least, look at this, at least. Why I say at least? Why I say at least? Yeah. Because you can only do worse than this one. You cannot do better than this number. You can only do worse than this n-1 number. Cannot be better than n-1 number. Worse, yeah, it's possible people do worse in their algorithms. They do some redundant comparison. How about that? Yeah. Some people, they design some algorithms, they may do some redundant comparisons. So they waste a few comparisons. That's possible. For example, for A less than B, B less than C, we do not have to do comparison between A and C, but one guy may still arrange one redundant comparison between A and C. That's the redundant comparison. Yeah. So we may have the situation people do redundant comparisons. Yeah. So that means the n-1 answer is the best. Yeah. The final answer greater or equal to n minus 1. And our current algorithm achieves this n minus 1 efficiency. How about that? Yeah, we get it. We do not have any redundant comparison. All our comparisons are necessary. No wasting comparisons. Yeah. That's the reason our algorithm is optimal. How about that? The convincing argument. So do you feel, yeah, so if people make this kind of arguments, then it should be convincing, right? It should be convincing. Yeah. Can you see this sequence of statements cover all the unknown algorithms, even unknown? It covers all those unknown algorithms, right? Yes. Here we find a key property, elimination property, right? Yeah. So one comparison can only eliminate one element. That's our key property, right? Yeah. One comparison can only eliminate one element in the array. Yeah. This property is so general, so it covers all those unknown algorithms. Yeah. So that's the reason we can study the optimality issue for all the algorithms that solve this, our problem number 3, find the minimum of an array. All right. So that is our final solution. We complete. No need to further improve this algorithm. It is already optimal. Not in our class, nobody can improve it. Not in this country, nobody can improve it. Not in the whole world, nobody can improve it. Even in future generations, forever, nobody can improve it by one comparison. How about that? How about that? This example. That's why at the beginning of this class, I said this question is very important in this class. Yeah. It is simple, but we need to use this question to explain many things in our later discussion. Yeah. All right, so I complete this subtopic. Yeah. Any questions so far? Yeah. Yeah. All right. If no question, I will move to next subtopic. Yeah. All right. D.2, comprehension question set number 1. Yeah. So I like to do a few comprehension questions, some examples. Yeah. Before you work on quiz questions, yeah, let me just give you some comprehension questions. Yeah. All right. The first one, no algorithm can be optimal because one can always improve a given algorithm. True or false? Yes. Based on our discussion, yeah, we spend a lot of time. Now, let us answer this question. No algorithm can be optimal because one can always improve a given algorithm. Think about it. Yeah. True or false? And why it is true, why it is false. Okay. Yeah. If you just use our previous example, then your answer is false, right? Yeah. Because in our previous example, we just completed, yeah, we have an algorithm and we proved it is optimal. here, the reason I designed this question, because many times people answer this question by their intuition. By their intuition, right? Yeah. By their intuition, yeah. Yeah, based on their everyday life experience. Yeah. People may feel, yes, we can always improve one particular algorithm. Yeah, we can do effort here and there to make it better. Yeah, yeah. Later you will see when we talk about improve an algorithm, it must be significant improvement. Significant improvement. All right. Yeah. Yeah. But in our previous problem number 3, minimal, that one comparison is significant. All right. But later in other questions, if your improvement is not significant, your improvement, yeah, you may do some 1 or 2 improvements, but we may not treat as significant improvement. Yeah, so that kind of understanding, yeah. After we study module 2, we will talk about significant improvement. What's the meaning? Why? Because sometimes people may do some minor improvement. Yeah, it's possible, minor improvement. But it does not count. It does not count because people treat that improvement is too little. Yeah, that's the main topic in our module 2. Yeah, here, let me just give you a little more information. Why is that? Yeah, in this particular problem, one is significant. Yeah, the situation is very special, but that example is not a general case. It's a special case, not a general case. For the general case, if you recall, we learned a term last time called a dominant term. Dominant term. When we get a dominant term, we ignore minor terms, right? We ignore many minor terms. Why we can ignore those minor terms? Because we treat them insignificant. They are not significant. Okay? Yeah. So we can ignore them. Yeah. So in our module 2, we will spend a lot of time to discuss about that issue. Okay? All right. So here it is still a little hard to understand. Yeah. All right. Okay, so that's the first question. Yeah. The second one, nobody can show that certain algorithm is optimal because you can not exhaust all the algorithms for solving a particular problem. Our second comprehension question. Yeah, let me read it again. Nobody can show that certain algorithm is optimal because you cannot exhaust all the algorithms for solving a particular problem. Second question. Yeah. So this one, we cut it in 2 parts, 2 halves. first half and the second half. Yeah. The first half, it is false, right? Yeah. By our problem number 3, our solution is optimal, and we made convincing arguments, quite convincing, right? Yeah. So if you do not feel it is convincing, then you can argue. You can argue with me, all right? Yeah. 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 We feel it is very convincing, yeah, and it is false. All right, yeah, that's the first half. The second half is correct, right? Yes, because nobody can exhaust all the algorithms for solving a particular problem. Nobody can exhaust. Yeah. Even our problem number 3, nobody can exhaust, right? Yeah. That's correct. Yeah. Yeah. But the problem is, when you connect these two halves, it is wrong. Yeah. Even if nobody can exhaust all the algorithms for solving a particular problem, but people can discover a property that covers all the algorithms for solving this problem. Yeah. Property, okay, yeah. Some special property, yeah. All right, yeah. So that means your logical reasoning is wrong. All right, yeah. The logical reasoning using second half to deduct the first half, that logical reasoning link is broken, is not right. Okay, yeah, yeah. So that's why it is false. Yeah. All right. So that's our second question. Yeah. Yeah. So here you can see from the first 2 questions, you can see our questions pretty tricky, right? Yeah. You need to really understand the materials well. Then you can answer the question correctly. Yes. Understanding, very important. Yeah. So I noticed some students, they do not study the notes, lecture materials, and they can answer my quiz questions. They use their intuition. They use their real life experience. Yeah. But you can see for questions like our first 2 comprehension questions, if some students rely on their real life experience, it is very likely they would make wrong answers. Yeah, think about that. For this class, we have many questions like that. So you need to study all the materials. Yeah. Yeah. All right. Yeah. So let's move to our third question. Number 3, given a polynomial. So this is a Horner's rule question, right? Horner's rule question, polynomial. Yeah. Horner's rule, related to Horner's rule. Okay. Yeah. All right. Yeah. Given a polynomial with the form, yeah, general polynomial form, yeah, is it possible that one can find a special case? Yeah, look at this phrase, a special case. I do not ask you the general case, I ask you the special case. Why is that? Because the Horner's rule covers the general case. Yeah. Here you can see there is a big difference. Special case, general case, big difference here. Yeah. All right. So is it possible that one can find a special case such that the number of multiplications to evaluate this polynomial is less than 4? Yeah. Why 4? Because based on the Horner's rule, yeah, our answer is the degree of this polynomial, that is 4. Degree of this polynomial, that's the number 4. Yeah. So based on the Horner's rule, our answer should be 4. Yeah. But now we are allowed to consider a special case. All right, special case. Yeah. Such that the number of multiplications to evaluate this polynomial is less than 4. Think about this question a little bit. Yes or no? Yeah. Doable. If it is doable, you need to find an example. Yeah. You only need to give me one example, one special example. For that example, the number of multiplications is less than 4, then you can claim the answer is yes. How about that? How about that? Is it possible? Think about that. All right. Yep. All right. Here, yeah. Anyone come up with some smart solution, some good example that can give you this answer here? Yeah. All right. Yeah, because we do not have much time, so let me give you the answer. Here I may like to mention that repeated squaring technique we learned last time. Repeated squaring technique we learned last time. Okay, yeah. By that, think about the monomial x to the 4th. This monomial, is it a special case? Yeah. x0, x1, x2, x3, all 0, and x4 equals 1. x4 equals 1, but x0, x1, x2, x3, all equal to 0. That's special case, right? Yeah. But when we do repeated squaring, we only need to do two multiplications. X times x, the first one. Okay. First multiplication. Yeah. Second, x squared times x squared, x to the 4th multiplication. How about that? Right? So the answer for this special example, the answer equals 2, right? Less than 4. How about that? So we have one example, less than 4. Yeah. All right. Even, actually, even if you do not use repeated squaring, when we do x to the 4th, if we do the direct way, the straightforward way, the answer is 3, right? Yeah, still less than 4. How about that? Straightforward way, yeah, less than 4. So that means your answer is yes. Think about that. Think about that. All right. Yep. Okay. Yep. All right. Yep. And here there is another interesting example. Yeah. Here. Yeah. Let me talk about another interesting example. P of x equals a0 plus a1x plus a2x squared plus a3x to the x cubed plus a4x to the fourth. In this one, in our previous one or two examples, we all consider x to the fourth, right? Yeah. That means a0, a1 through a3, all zero. Yeah. Here, I want to add one assumption here. Okay, add one assumption here that all these coefficients, okay, are non-zero. How about that? I do not allow you to use any zero coefficient. I do not allow you to use any zero coefficient. All right? Yeah. Yeah. In that case, we avoid monomial case. Simple monomial case. Now the question, is it still possible for us to find answer of our comprehension question number 3 in the previous slide? Yeah. Here. Yeah, I just modify the previous question by adding this assumption. I add this assumption. None of the coefficients could be zero. I add this condition. Then I'll ask you that question again. Yeah, think about that. Yeah, that will make the question a little harder. Yeah, yeah, yeah. Here I talk about that because to answer that question, you need a little more knowledge to answer that question. Knowledge is also important. You need to have that critical piece of knowledge to answer this question. First, the answer is still yes. But the example is a little harder to get. All right, yeah. Let me write that example and see if you know the key point in this example. Yeah. All right, so let me write this polynomial. Yeah. P of x equals 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. How about that? None of the coefficient is zero, right? All non-zero. Here, I want to say, to find the value of this polynomial, I can use fewer than 4 multiplications to do it. I claim that. This is my example. Can you see that? Can anyone see? Why is that here? Yeah, this is an interesting example. All right, yeah, okay. Yeah. All right. That's what I mean. We need some critical piece of knowledge in order to answer this question. What is good? Yeah, good. The student, yeah, we only need to factor 3 times. Yeah, the direction is correct. Yeah, the direction is really correct. All right. Yeah, but you need to do a lot of work, right? Yeah. But here I want to point out a famous formula. if you heard of that famous formula. All right, okay. Yeah, there are several names you can, one is binomial formula. Binomial formula. That is one. Another is called Newton's formula. This part, the knowledge part belongs to your discrete math. Discrete math, yeah, the topic in your discrete math. Yeah. So you can find a formula, the binomial formula, Newton's formula, that is this. A plus B to the nth power equals A to the nth. Then the combinatorial number. You know the combinatorial number, right? Yeah, all right. So n choose 1, A to the n minus 1. Some people also write C sup n sub 1, yeah, like that, okay, yeah, dot, 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 all right, yeah. N choose n minus 1, A, B to the n minus 1 plus B to the n. Yeah. This is the so-called binomial formula or Newton's formula. And here we use A equals 1, B equals X, N equals 4. So 1 plus 4 choose 1, that is 4 X, right? N choose 4 choose 2, 4 choose 2 equals 6. I hope you can know how to calculate the binomial or not combinatorial number. Yeah, these things, combinatorial number. Numbers. That's your discrete math content. All right, yeah. 6x squared plus 4x cubed plus x to the 4th. How about that? Yeah. If you apply binomial formula or Newton's formula, you will get this expression, 1 plus x to the 4th. How many multiplications you need to find the value of parenthesis 1 plus x to the 4th power? The answer is 2, right? How about that? Repeated squaring, the best answer you need 4. Okay? Yes. Think about that. Think about that. All right. Yeah. Yeah. Here, another important thing, yeah, I may like to mention related to this example. This example. Any one of you heard of one special structure? It's called a Pascal's Triangle. Pascal's Triangle. Yeah, this another famous concept, Pascal's Triangle. Yeah, think about that, Pascal's Triangle. Okay, yeah. Here, let me talk about a little bit that Pascal's Triangle. Okay, all right, yeah. All right, I need to, yeah, here, let me use, yeah, we are near the end of this class. We just have a few minutes. Let me talk about this Pascal's Triangle. It's pretty interesting. That is related to our comprehension question number 3. Yeah. Regarding the Pascal's Triangle. Yeah, this concept. All right. Yeah, so you can search the web to study this topic a little bit. All right. that is about the coefficient of a plus b to the nth power. Okay, if we list the coefficient of this binomial, yeah, this is the binomial. You can look at that. Yeah. First, when n equals 0, a plus b, that's 1, right? Yeah, because a plus b to the 0th power, that is 1. So we put that 1 coefficient on top of the tree. Yeah, top of tree 1 put there. All right. When n equals 1, we list that a plus b to the first. Yeah, that equals a plus b. So you can see a coefficient is 1, b coefficient also 1. So we put it after the top level, 1, 1. Yeah, all right. N equals 2, we know a plus b squared equals a squared plus 2ab plus b squared, right? So then we list the coefficient 1, 2, 1, next level 1, 2, 1. All right, yeah. So you get a triangle, and n equals 3. So we do this a plus b cubed. So a cubed plus 3a squared b plus 3ab squared plus b cubed. All right. So you get coefficients 1, 3, 3, 1, and we put the next level 1, 3, 3, 1. Yeah. With these example, so then you can find it has this kind of property. Every number, for example, 2 here, it is just sum of 2 numbers on its shoulder of the previous level, higher level. Yeah, 1 level higher, 2 shoulder numbers on 1 level higher of this number. Yeah. All right. Yeah. 3, 1 plus 2. All right. 2 plus 1, 3. Yeah. So, and 1. Yeah. Because you only have 1 shoulder number. So 1. All right. The next level, based on this structure you just discovered, 1. Yeah. How about 1 plus 3? So 4. How about 3 plus 3? 6. How about 3 plus 1? 4. And 1. All right. Think about that. 1, 4, 6, 4, 1. That's the example I used in the previous slide. Right? Yeah. If you go to another level, 1, 5, 10, 10, 5, 1. This line, this level corresponds to n equals 5. So these coefficients corresponds to a plus b to the 5th. How about that? Okay, how about that? Yeah. This structure is called Pascal's triangle. Yeah. These numbers, all these are the combinatorial numbers. All these combinatorial numbers can be organized in this triangle structure with the relationship between 2 adjacent levels as the one I just described. Yeah. Pascal's triangle. Yeah. All right. So here I talk about this special structure. Yeah. Try to understand this structure. Yeah. If you feel it's pretty interesting, you can do some web study on this topic. Yeah. Otherwise, based on this information, the reason I spend a lot of time on this question, you can imagine, yeah, more than 10 minutes. I spend more than 10 minutes on this topic, Pascal's triangle. Yeah. Then you can imagine later, I may give you several questions related to Pascal's triangle. All right, yeah, so that's all we need to do today. Yeah. Although I have a topic, repeated cubing. Yeah. So I will talk about that later somewhere when I feel appropriate. Yeah. Later, if I have 10 minutes slot, I will put there repeated cubing technique. Yeah. So other than that, we complete this whole module 1. And also we complete today's class. If you have any question, you just